Have you ever wondered how some cars achieve that impressive acceleration that pins you to your seat? Today, we're going to uncover the secret behind this power, the turbine. Let's explore how this amazing component transforms car performance and why it's so fascinating. Imagine being in a car that seems to come alive with every press of the accelerator pedal. That's what the turbine does. Let's find out how. Everything starts with the engine. In a conventional internal combustion engine, air enters the engine, mixes with fuel, and this mixture is burned to generate the power needed to move the car. However, there's a limit to the amount of air that can be naturally sucked in by the engine. This is where the turbine, or turbo, comes into play, revolutionizing this process. The turbine is essentially a forced air pump that compresses the air entering the engine. It consists of two main components, the compressor and the turbine itself. The compressor is responsible for pulling more air into the engine, while the turbine is driven by the engine's exhaust gases. When you press the accelerator pedal, the exhaust gases produced by the combustion of fuel in the engine are directed to the turbine. These high-pressure, high-temperature gases pass through the turbine blades, making them spin. The turbine is connected to the compressor by a shaft. So when the turbine spins, the compressor also spins. The rapidly spinning compressor sucks air from the environment, compresses it and sends this compressed air to the engine. This compressed air is denser and contains more oxygen. When this denser air enters the engine's cylinders, it allows more fuel to be burned during combustion. Burning a larger amount of fuel generates more power, resulting in much greater acceleration and better car performance. To better understand, imagine your car's engine is like a wood stove. An engine without a turbo is like trying to light a fire with little air. The fire will burn, but it won't be very intense. Now add a turbo, which is like using bellows to blow additional air into the fire. With more air, the fire burns much stronger and hotter. Similarly, a turbo engine burns fuel more efficiently and powerfully. But it's not just about pushing more air into the engine. The amount of compressed air must be carefully controlled to avoid damaging the engine. This is where the wastegate, a valve that regulates turbo pressure, comes into play. When the pressure reaches a certain level, the wastegate opens and redirects some of the exhaust gases, preventing the turbine from spinning faster than it should. This ensures that the turbo pressure remains within safe limits. Another crucial component in a turbo system is the intercooler. Compressing the air heats it up, and hot air is less dense, which is counterproductive for the turbo. The intercooler cools the compressed air before it enters the engine, increasing its density and, consequently, the engine's efficiency. Besides increasing power, the turbine also improves fuel efficiency. Turbocharged engines can be smaller and lighter than naturally aspirated engines with similar power, resulting in a lower overall vehicle weight and better fuel economy. Turbines are not exclusive to sports cars. Many mass-produced cars, trucks, and even airplanes use turbocharger technologies to increase efficiency and performance. Recently, technological advances such as variable geometry turbos and electric turbos have allowed even more control and efficiency, reducing the famous turbo lag and providing a faster and smoother response. How it works. Let's explore how a turbine works in a car. The turbine, or turbo, is a component that increases the amount of air entering the engine, resulting in more power. The process starts with the exhaust gases generated by combustion in the engine. These hot, high-pressure gases are directed to the turbine through an exhaust manifold. When the gases hit the turbine blades, they make it spin. The turbine is connected to the compressor by a shaft, and when the turbine spins, the compressor also spins. The compressor is responsible for sucking air from the environment, compressing it and sending it to the engine. By compressing the air, the compressor increases the amount of oxygen available for combustion. More oxygen means more fuel can be burned, resulting in more power generated by the engine. However, compressing the air also heats it up, which can be counterproductive. Therefore, the compressed air is cooled by an intercooler before entering the engine cylinders, further increasing its density and efficiency. To control the amount of compressed air entering the engine, there's a valve called a wastegate. The wastegate regulates the turbo pressure, opening to release some of the exhaust gases when the pressure reaches a certain level. This prevents the turbine from spinning faster than necessary and protects the engine from damage. Additionally, modern technologies like variable geometry turbos and electric turbos help minimize turbo lag. Variable geometry turbos adjust the turbine blades to optimize speed under different operating conditions, while electric turbos use electric motors to accelerate the turbine instantly, providing a faster and smoother response. In summary, the turbine works by using the energy of the exhaust gases to spin a compressor that pulls and compresses air from the environment, increasing the amount of oxygen available for combustion in the engine. This results in more power and efficiency, transforming the vehicle's performance. Benefits. The benefits of using a turbine in a car are numerous and significant, impacting both performance and vehicle efficiency. First and foremost, the power increase is one of the main attractions. The turbine allows the engine to burn more fuel by providing a larger amount of compressed, oxygen-rich air. This results in more efficient and powerful combustion, providing faster acceleration and superior performance, especially in smaller engines that otherwise couldn't reach such power levels. Besides the power gain, fuel efficiency is also improved. Turbocharged engines can be smaller and lighter than naturally aspirated engines, producing the same amount of power. This reduction in engine size and weight contributes to better fuel economy since the vehicle doesn't need to carry a larger, heavier engine to achieve the same performance. In terms of consumption, this means turbo cars can be more economical, offering better mileage per liter of fuel. Another significant benefit is the reduction of emissions. Turbocharged engines can be tuned to burn fuel more completely and efficiently, resulting in lower emissions of polluting gases. With increasingly stringent environmental regulations, this improved efficiency helps car manufacturers meet emission standards and contributes to a cleaner environment. The versatility of the turbine is also a strong point. It can be applied in a wide range of vehicles, from high-performance sports cars to mass-produced vehicles and trucks. In sports cars, the turbine provides the extra power needed for exciting performance. In mass-produced vehicles, it offers a way to improve fuel efficiency and emissions without sacrificing power. In trucks, it allows smaller, more efficient engines to provide the power needed to haul heavy loads. Furthermore, continuous technological advancement in turbochargers, such as variable geometry turbos and electric turbos, has further enhanced the benefits of turbines. These advances allow for a faster turbo response, eliminating the infamous turbo lag and providing smoother, immediate acceleration. This results in a more pleasant and responsive driving experience, regardless of driving conditions. In summary, the benefits of using a turbine in a car include a significant power increase, better fuel efficiency, reduced emissions, wide application versatility, and an improved driving experience thanks to technological advances. These combined factors make the turbine an attractive choice for improving the performance and efficiency of modern vehicles. Curiosities. Turbines in cars have several interesting curiosities that highlight their importance and impact on automotive engineering. To begin with, the concept of turbocharging is not new. In fact, it was initially developed to increase the power of aircraft engines during World War I. Engineers realized that air compression could compensate for the performance loss of engines at high altitudes, where the air is less dense. This fundamental principle was eventually adapted and refined for land vehicles, transforming car performance. Another fascinating fact is that the turbine works on the principle of energy reuse. In a conventional engine, exhaust gases are simply expelled through the exhaust system, wasting the energy contained in them. However, in a turbocharged engine, these gases are redirected to spin the turbine, which in turn drives the compressor. This energy recycling process contributes to the overall efficiency of the engine, making the most of every drop of fuel. The influence of Formula One on turbo technology is undeniable. In the 70s and 80s, Formula One saw the peak of turbocharged engines, with cars reaching extraordinary power levels, often exceeding 1,000 horsepower in qualifying configurations. This period was crucial for the development and popularization of turbos in production vehicles, as many of the technologies and innovations created for the tracks eventually made their way into street cars. Turbos are not just for sports and high-performance cars, they are also widely used in passenger cars and even utility vehicles. The need for fuel efficiency and emission reduction has led many car manufacturers to adopt turbochargers in smaller engines. These engines, often called downsized, can offer the same power as larger engines but with better fuel economy and lower CO2 emissions. Another interesting curiosity is the characteristic sound of turbocharged cars. The whistle or whistle heard when accelerating a turbo car comes from the air being compressed by the compressor and the operation of the relief valves, which release excess pressure when the throttle is quickly closed. This sound has become iconic among car enthusiasts and is often associated with high performance. The phenomenon known as turbo lag is also an intriguing part of the turbo world. Turbo lag is the delay between the moment the driver accelerates and the moment the turbo starts providing additional pressure. This delay occurs because the turbine needs time to accelerate enough to start compressing the air effectively. Recent advances, such as variable geometry turbos and electric turbos, have been developed to minimize this lag, providing a more immediate response. Finally, it's interesting to note that turbos are not exclusive to gasoline cars. They are also widely used in diesel engines. In fact, turbocharged diesel engines are extremely common in commercial vehicles and trucks, where the combination of high torque and fuel efficiency is crucial. These curiosities highlight not only the complexity and sophistication of turbines but also their importance in the evolution of automotive engineering, from their origins in aircraft to their application in a wide variety of modern vehicles. The use of turbines in cars represents one of the most significant innovations in modern automotive engineering. The turbine, or turbo, works by harnessing the engine's exhaust gases to spin a compressor, which sucks in and compresses ambient air, sending this compressed air to the engine. This process allows for more efficient fuel combustion, resulting in a significant increase in power and performance. One of the main benefits of turbines is the increase in power. Engines equipped with turbochargers can generate more force without significantly increasing the size or weight of the engine. This is particularly advantageous for manufacturers seeking to offer more powerful vehicles without compromising fuel economy or emissions. Fuel efficiency is another strong point of turbines. Turbocharged engines can extract more energy from each drop of fuel by optimizing the air-fuel mixture entering the cylinders. This means that even smaller engines can offer performance comparable to larger, more fuel-thirsty engines, providing better fuel economy and a smaller carbon footprint. The versatility of turbines is impressive. They are not only limited to high-performance sports cars, but are also widely used in mass-produced vehicles, trucks, and even airplanes. This wide applicability demonstrates the effectiveness and efficiency of turbines in improving performance and efficiency across various types of vehicles. The history and evolution of turbines are also fascinating. From their origins in military aviation during World War I to their widespread adoption in street cars, turbochargers have undergone several phases of development and innovation. Technological advances, such as variable geometry turbos and electric turbos, have continued to enhance the response and efficiency of turbocharged systems, minimizing issues like turbo lag and providing smoother and more immediate acceleration. Turbos have also significantly contributed to the reduction of vehicle emissions. Turbocharged engines can be tuned to burn fuel more completely and efficiently, resulting in lower emissions of polluting gases. With environmental regulations becoming increasingly stringent, the ability of turbos to help manufacturers meet these standards is invaluable. Beyond the technical and environmental aspects, turbines have an emotional appeal among car enthusiasts. The characteristic sound of the turbo, the power boost, and the sensation of quick acceleration create an exciting and engaging driving experience. For many, driving a turbocharged car is not just about performance but also about the thrill and connection with the machine. In summary, turbines have transformed how engines work, providing a unique combination of power, efficiency, and driving pleasure. Turbocharging technology continues to evolve, promising even more innovations in the future. Whether in sports cars, mass-produced vehicles, or trucks, turbines play a crucial role in shaping the future of mobility, making vehicles more powerful, efficient, and environmentally friendly.